Thanks very much. I want to talk a little bit about some of the work we've been doing at Horizon on advancing the state of quantum programming. So at the moment, quantum computing, where it's at least where the software layer is at, is still like computing in the 1940s or 50s. We're still piecing together programs, one logical operation at a time, although we're starting to see libraries of algorithms that you can use, and they're easier to use because you can access them through Python and so on. We're still missing a lot of the core software infrastructure to enable actual complex software, to enable things like memory management and so on that are fundamental to how a conventional computer works today. So what we're doing at Horizon, we're trying to build a complete toolchain all the way from classical code that you can run on a conventional computer, to an accelerated implementation on a quantum computer. And what I'm focusing on today is the second part of this process. So first we need to take a classical program, we need to break it apart, break apart the recursion, break apart the control flow in it into simpler and simpler elements, recognize them, try to replace them with quantum structures that do the same thing. And if we put them all back together, that gives us a kind of high-level description of a quantum program. But the next part you have to do with this, you need to go from that high-level description of a quantum program, and you need to compile it down into something you can run on hardware. You need a runtime environment that can accidentally execute that code. And then you need to be able to package it in some way that the user can actually make use of it. And for us, the endpoint for us is kind of wrapping that up and deploying it as an API. So I'm going to focus on this second half, going from the high-level description of a quantum program to deploying it on quantum hardware, and progress we've been making over the last year. All of these are built currently in our integrated development environment, Triple Alpha, where you can write quantum programs, you can code, you can compile them down to target hardware, you can deploy them on real systems, and you can also do things like resource counting. What we do, our approach to quantum programming is different than basically everyone else. So if you look at how quantum programming is done today, many of the frameworks that exist have been built bottom up, basically looking at the hardware that's available that they're trying to program and exposing its capabilities. And as new capabilities come along, they need to be extended to expose more and more capabilities of the hardware. We go the other way around. We go top down. So we target a kind of idealized quantum computer. And we try to build a runtime environment that can make that code run on today's systems. And that really leads to a difference, a fairly large gap in terms of capabilities of what you can express, what you can do in our languages, versus what you can do trying to construct programs gate by gate. In particular, the way we think about this idealized quantum computer of the future that we have in our minds, it's not really just a QPU. Rather, it is the combination of a QPU and a classical computer that acts as the control systems. So the classical computer is deciding what operations get sent to the QPU. The QPU is executing those operations, but concurrently, there might be more classical computation going on. And in particular, the QPU is sending back results to the classical control system, and the classical control system is taking that into account. So maybe we are going to apply operations that are conditioned on measurement results we've previously seen. So if we take that system together, that gives us something more powerful than a QPU that can just evaluate circuits. It allows us to do arbitrary control flow. It makes it much more like conventional computers. But there's another part to this, which is that you also need to think about how this system interacts as part of an environment. So you need to be able to do input and output to other systems. You need to be able to communicate over a network to read in data from some system, to get user input, whatever it is that needs to happen. And that is precisely what we're trying to target. This is the system we are trying to program. And you can say to me, well, this isn't how my quantum computer works today. And I would agree. A lot of the systems don't work quite like this today. So in order to do this, to make our code that is targeting this abstract machine, to be able to make it run on today's systems, we also need to be able to build a runtime environment that's capable of evaluating these branching programs on today's QPUs. So the way we view this, the basic idea, how we approach this, is that at the lowest level, our programs are broken up into blocks. Within each block, there's some set of quantum and classical instructions. This might be evaluating classical functions on either on control hardware or on classical compute resources. Then we need to be able to perform operations on the QPU as well. So those blocks also need to be able to contain instructions to the QPU. You know, do a Hadamard on this qubit, do a C0 between these two qubits, and so on. But these blocks are strung together in such a way that at the end of each block, there's an instruction that tells you how to choose the next block. And that allows you to do arbitrary control flow. You can implement indefinite loops. You can do things like while loops. You can do if statements. You can do all sorts of things. You can also wait for I/O from other systems. But you need to be able to execute this on hardware. And we have two ways of doing that. So one way is we can try to actually run it in real time if the control systems are sufficiently capable to try to do this. But more often, a lot of the systems that we have currently set up in Triple Alpha are not capable of this. So instead, we have to use them to evaluate circuits. So what we do is we take our program that is given by this kind of directed acyclic graph. Sorry, it's not a acyclic graph, it has cycles in it. We have this control flow graph that has these blocks within it. We basically try to simulate the effect of the control systems to run the program as far as we can in kind of simulating just the control systems to get out a large circuit that we can then evaluate to obtain the information that we didn't know to be able to unroll the program further. And this gives us a kind of hybrid execution where we evaluate circuits of varying sizes to allow us to simulate the effect of completely arbitrary control flow. So we call this kind of our near-time runtime environment. But we would really like to get to a point where we can do real-time execution on as many systems as possible, where we're able to directly implement our programming languages without the overhead of having to do the post-selection of stitching these various circuits together. These capabilities make Triple Alpha, make our programming languages, Helium, which is kind of a basic-like programming language, and Hydrogen, they make them kind of an ideal sandbox in which to experiment with fault tolerance ideas and quantum error correction, because they allow you to do that classical compute in parallel with your quantum computation to decode your syndrome qubits. They allow you to apply corrections conditioned on the output of that classical computation. And yes, this is stitched together by a near-time runtime environment, so it's not executing with a single call to the QPU, but rather several. But this really gives a nice place to experiment with fault tolerance, experiment with error correction. And if you come along same time tomorrow, there's a talk from Entropica Labs and us showing some of the work Entropica have been doing building an error correction stack on top of our tools. But what I wanted to talk about today is some advances we've made in these tools. And as we go in this direction, as we start to look at these branching programs rather than just static circuits, we get into many of the same kind of foundational problems that you have in the very earliest days of computing when you start to look at general programming languages. In particular, if you have this control flow graph, if you're implementing a programming language that's Turing complete, it may mean that the amount of memory used is not computable. You may not be able to enumerate all of the qubits that are going to be used ahead of time. You may not be able to label them. You may not know which ones will be available when. And this means you need to be able to manage that on the fly. So we've been able to build into our system for the first time, I think it's the first time ever done for quantum computing, dynamic memory management. So that within our programming languages, you can request a qubit. So in this case, you can see the sample on the left says qubit to A. So the variable A will contain the address of a qubit that is generated dynamically on the fly. It's just allocated as what is a free qubit in the device at this current point in time. And then when we're done with it, we can free it. So you see the instruction free later. And this is directly analogous to malloc and free in C, when you're getting the system to dynamically allocate memory to your program, and then you're freeing it up for reuse. And if you look at the program on the left, when you compile it down, you can see the program on the right here. The result of this is that there are two qubits in the original program, A and B. But because we free up A, the same qubit gets put back on the stack, gets reused, and so the operations, if you look at them, have now been performed all on the same qubit. So in this case, qubit 7 has been assigned for both of those variables. And the program does exactly what it's supposed to do, right? So it has exactly the same performance as if we had used different qubits for them. We've also enabled addressing of particular fixed physical qubits. So if you, instead of saying qubit to A and getting a virtual qubit, you say qubit to underscore and a number, it will directly address that physical qubit on the chip. You know, depending on which chip you are, the qubits are going to be labeled differently. There will be some connectivity graph between them, but you can pin physical qubits if you want. So you can see an example here on the Rigetti Anka 9Q, and you can see an example of, in this case, qubit 1 being pinned. But you can also mix these with virtual qubits. So I can say qubit to A, and I can say qubit to underscore 1, and that means one of those qubits is going to be fixed as underscore 1, and the other one will just be assigned wherever it can fit on the chip at that point in the program. So this is quite powerful. It allows us to target particular physical systems on the chip, or to allow everything up to the compiler and to the runtime environment to assign on the fly. We've started to add new backends that bring us beyond the gate model of computation, in particular to do measurement-based computation. So at the moment, we can output circuits to many different kinds of quantum processors, many different gate sets. But now we're going to a model beyond, that takes us beyond gates entirely, so the measurement-based model. So in this framework, in this model of computation, all of the computation is done by first entangling a large quantum state called a resource state, and then the computation proceeds by making measurements, single qubit measurements on that resource state. There are no entangling operations done. There's no CNOT gates, anything like this. Everything is implemented just with single qubit measurements, generally in the XY plane. So you can do this now within our system. You can select the MBQC backend within our compiler and compile down to it. If you do that, the net result of this is going to be a combination of two things, like you can see on the right-hand side of the slide here. On the top half, you've got the state preparation instructions. So you'll see the qubit preparations, then Hadamards that put them in a plus state, and then edge operations that do the entanglement into the graph state to make the resource state. And then the rest of the computation is the feed-forward logic. This is all classical computation and measurements, so determining the basis for measuring each qubit as you go. And this opens up not just systems like superconducting and trapped ion systems, but it opens up now photonic systems as well, where a lot of the time you're creating a graph state, you're creating a resource state, and then implementing the computation as measurements on it. Another advantage to this is it's a core building block of many of the secure delegation protocols, and that's something we want to enable with this. Now, within our toolchain, what we've been able to do is not just construct measurement-based computations, but also to do optimization by eliminating the Pauli basis measurements. So anything that is measured in the X, Y, or Z plane can be eliminated from the graph. So this is an example of the Deutsch-Jozsa algorithm. This is the circuit. Then here you see the graph state that is a result of compiling that directly. And here you see the, beside that, you see it after Pauli elimination. The number of qubits is drastically cut down. The number of operations is drastically cut down. And again, this is the generated code here. So the generated code is just much more compact than it would otherwise be. And if we do this on something like Grover's oracle with Grover's algorithm with an oracle we generate from C, you see a pretty big reduction. So in this case, a 77% reduction in terms of the number of qubits, number of measurements that need to be made when we do this Pauli elimination. The next thing that we've done has been a really big advance for us, which is to introduce, to take our programming languages that give you quite high-level control, allow you to do arbitrary control flow, allow you to hook into APIs to read in input from the user and output to the user through an API interface. And we've added pulse control to this, so that you can use the pulse control at any level within the system, not just at the lowest levels, but you can still use the high-level constructions, the subroutines, the while loops, all of those kind of things that you have at the higher levels in Helium and so on within our programming languages. So this is an example of it here. You can define your own pulses. Or you can use pulses from a library we have already written, so drag Gaussians and different kinds of things like this. Once you've defined the pulse you want to use, you can then construct commands from these that are either for a single pulse or for multiple pulses, defining the dimensionality of the system it's acting on, defining the parameters it's going to take, as well as the pulses, the sequence of pulses or a set of pulses that give that one command. So it might be a single pulse, it might be multiple pulses. And then you can write these directly into our code. You can write in the parameters, and you can compile that down, run it on hardware. This makes it quite easy to implement things like calibration routines. So for example, if we want to do Rabi oscillations, we can do it with a couple of lines of code. We're able to take in as input from the user various parameters, such as the duration. We can compile it down, hit deploy on this, and we will get back an API. And that's kind of what you see here. That API endpoint we can trigger to run this on hardware. And it will request from us the duration. So we say the duration, and we can use this then as a backend within, for example, a Python script to be able to generate Rabi oscillations and so on directly just by calling this API, rather than having to go through the quantum program each time. We just have a single simple API that we can bake in to call to give us these kind of calibration things, details. Not just at the point of doing things like a single point on the Rabi oscillation, but we can bake in the calculation for the whole cycle. We can work out T1, T2, so we have an API that just returns these figures of merit to the user. Here are some more examples. It's pretty straightforward to do this within our system. If you want to see a demo, please come by the stand. Denny's there, he's showing them every coffee break and lunchtime. We've got time booked on the Rigetti system, so you can see it run live. Now, with that, where we get to is a point where we're able to target down to really quite low level, down to the pulse level and multiple hardware backends. But now we're in a situation where we're programming in, at one level, a pretty high level, working in maybe a different instruction set than the instruction set we're going to get down to when we want to target a piece of hardware. So all of this has been done in a kind of hardware agnostic way, except by the time you get to the pulse level, you're specifying which pulses go to which lines, and it's no longer hardware agnostic at all. So what we need to think about is how do we optimize our programs where they might be written in one instruction set, but run on hardware that's in a different instruction set. And one of the things we've put a lot of effort into with this is optimization, circuit optimization. And in particular, developing a system that allows us to do optimization that is entirely independent of the gate set that the program is written in. It works with absolutely any instruction set you can think of. And basically, it works like this. You can construct what you want to optimize against, your fitness function, by dragging various different figures of merit into a ranked list, and it will try to optimize against that. And you can set some priority level, and the higher you set it, it's going to take longer to compile, but you get a better program out. But the way we have built this is such that it discovers the identities that allows us to do simplification automatically. So it doesn't know things like the Euler decomposition, that 3 rotations are enough for me to do any single qubit unitary. Instead, it figures that out on the fly. It sees, hey, this sequence of gates, there are multiple different replacements we could make for it that it has enumerated. And it works out the best one based on that fitness function that we've prescribed in the optimization panel. It is also general enough that it's able to work out these simplifications even with noisy operations. So in this case, here you can see an example where it is discovering that it can simplify 2 dephasing operations into a single dephasing operation. And it doesn't know any of this beforehand. It doesn't know anything about the group theoretic structure of quantum computation beforehand. It only knows what commutes and doesn't commute, and a mathematical description of the action of each of these operations. What we're doing now, as we've gotten to this point where we've gotten the system, really a fairly complete programming stack all the way from high level code all the way down to pulses targeting hardware. The next thing we need to do is put this all together, to put together a system that's actually able to do a real-time implementation of our programming languages, to have a real-time runtime environment for it. So we've taken the step of building out a hardware testbed in Singapore. We have our first chip from Rigetti, an Avera QPU. The fridge is coming in a couple of months, and we hope to have it cool by March. So we hope to be able to start executing this directly on hardware that we control, full stack, full software stack down to hardware in the very near future. So with that, I will leave you to it. Thank you very much for your attention. And if you're interested at all in seeing our tools, please stop by the stand, or you can sign up for early access using this QR code. Thank you very much.